Hello. So today's video will be the review of circular motion and gravitation. Again, this is a short one. I'm only going to go onto one page with what you need to know for this topic. So first of all, the one kind of key equation here is that centripetal acceleration, A sub c, equals v squared divided by r. Notice that we square velocity here, so we lose the sign of velocity, but that's no problem because this already tells us direction. Because direction is always to the center of the circle when something is in uniform circular motion. And then we can put a few things together. This is the one the AP gives you. But if we do this, we have this, and we have this equation. The typewriter version of Newton's second law, we can say that the centripetal force equals mv squared divided by r. And then we have another equation. So we have this so far, and this. For two equations we can use to solve problems. Let's continue. Kind of go to another section here. From dynamics, we can get this equation, basically the gravitational version of Newton's second law. But we also have the universal law of gravitation, Newton's formula, like such. Note that they're both F sub g, F sub g. So what we can do, of course, is make them equal to each other. We can say F g equals F g. So m, and this is going to be m1. Mass cancels. And you have little g, it's the acceleration due to gravity, equals big G. Now a big M, because this would be the mass of the, likely the star that a planet in its orb, never mind. Likely this would be the mass of the planet you are on. And then the radius squared, you are from the center of it. This is also given on the AP sheet, but not in a really useful form that can be easily solved. So this would be used, for example, it says, what if you were on a planet that was twice the mass of the Earth? What would be the acceleration due to gravity? And you could easily solve that with this formula. So let's put a box around that one. This one's really important. And then let's go on. Let's do a simple picture. So let's say we have a star, like the sun, at our center of our picture, and that we have a planet in orbit around it. That planet is actually only feeling one force, and it would point towards the center, and we could label it Fg, the force due to gravity. But of course, this is also the centripetal force. So we can say this, Fg equals Fc, and do some more funny business here to derive Kepler's third law. But before we do that, there's another important equation. So we know that velocity equals displacement times time. There's a uniform circular motion version of this equation, and that's v equals 2 pi r, which is the circumference of a circle, divided by big T, which is the period. So we'll end up using that, but it's an important equation for other applications too, and you should have. So let's do some work here. So and again, this would be the M1 on here. Mass cancels. Let's get rid of the R's. I end up with big G, and this goes to a big M equals V squared times R if I multiply both sides by R squared. Then I'm going to substitute this into here. So big G M equals 4 pi squared R now cubed over T squared. My next step is I'm going to multiply both sides by T squared and then divide by GM. And here is where we end. And this is kind of our version of what's known as Kepler's third law, which relates the period of an orbit to its radius. The period squared is going to be proportional to the radius cubed. And we can derive that out using here. So to review, centripetal acceleration, the centripetal force, the acceleration due to gravity, no matter what planet you're on, your velocity equation for uniform circular motion, and deriving out Kepler's third law for this type of situation with a planet in orbit.